the absolute zero, it's 0 Kelvin or minus 273 degrees Celsius. That's why we have to use different material to measure the temperature. We call it the thermometer, and we have here different thermometers to be comparing each one from the other. We have here Kelvin, we have Celsius, we have the Fahrenheit. To change it from the Kelvin to Celsius to Fahrenheit, we have to mark the degrees for each one. And we take the water as a standard material to work on. The degree Celsius is having two major marks where we can define the changes of the temperature. 0 degrees Celsius means that the temperature or the degree where the water starts to freeze or melt. 100 degree, it's the temperature or the degree where the water starts to evaporate or condensate. It's equivalent, the two marks 100 and the 0 equivalent to the Fahrenheit when the Fahrenheit is 212 and the 0 it's when the Fahrenheit is 32. The same for the Kelvin. 100 degrees Celsius equals 373 Kelvin. 0 degrees Celsius equals 273. That's why when I want to generalizing the equations to get or go through it between the Kelvin and Celsius and also Fahrenheit, we said that we will remove the 0 for each one and we will add the minusing mark of the 0 in other area for thermometers. The 0 for Celsius, it equals the Kelvin minusing 273, which also equals the Fahrenheit minusing 230, sorry, minus 32 only. The 100 here for Celsius, it's the same for Kelvin to be 100, and for the Fahrenheit, it equals 180. To describe this, you have to go through it here on the area down. Okay, when the Celsius is at the Celsius, when you are minusing with a 0, it gives you C, and also a 100, it equals minus the 0 to gives you a 100, which means you have removed the two marks from each point at the thermometer. The thermometer here, the 0 is 273, the 100 is 373. So the Kelvin minusing 273, which the 0 on Celsius, equals 373 minus 273. So you are removing the freezing point from the boiling point. Okay, the same happens here. So 32 minus 220, which gives me 180. If I want to change it from Kelvin to Celsius, if you want to get a degree with Celsius, you have to remove 273 from the Kelvin degree. And if you want to change from Celsius to Kelvin, it's adding the 273 to the Celsius. For changing from Celsius to Fahrenheit, you have to use this equation, 5/9 multiplied by Fahrenheit minus 32 to give you the Celsius. And the Fahrenheit here equals 9/5 multiplied by Celsius plus 32. This is to change it from Celsius to Fahrenheit. I have to take care of this. This page is very important. Okay. So if we want to through it, what are the ways of transferring the thermal energy? There are three: conduction, convection, and radiation. Conduction happening when two objects are transferred or directly attached or contacting each other. And the convection here happens when the mass motion of the molecules and they are transferred, where the hot objects are traveling to the top, cold objects are moving down. Radiation here, it doesn't need any kind of conduction, no direct, no indirect. It's moving with electromagnetic radiation, and the waves that are moving with electromagnetic, they are using the energy to be transferred with it. He said here convert the Celsius into Fahrenheit. We can find here the actions and also the work. And we have here also another work. We went through this. We go here for the heat, internal heat, and the difference between both. Heat here is the energy that is transferred by the object body from one body to another body, which causes difference in the temperature, which means it moves from the hot objects to cold objects. Internal energy, it's total random kinetic energy of the particles of the substance plus the total interparticle potential energy of the particles. So the sum between both kinetic and potential for internal materials, it causes for us the internal energy. The internal energy of the system can change as a result of heat added or taken out and as a result of work performed. Okay, that's why there is a term comes out, we call it specific heat capacity, C, of anybody. It's energy required to increase the temperature of a unit of mass of the body by only 1 Kelvin. So, amount of heat required to increase the object to 1 Kelvin, we call it specific heat. You can find here at this table that the specific heat for each material is different from one another, which means the amount of energy needed to increase only 1 Kelvin, as an example for the water, it needs 4,200 joules. When you are comparing to the others, it's different from part to another part. How to change the phases of any material? It's by adding or removing the heat. You have to change the particles movement inside it. That's why you can find that it's changed from a phase to another phase. We have here melting, freezing, evaporation, condensation, and sublimation. Melting when the solid changed to liquid, freezing when the liquid changed to solid, evaporation when the liquid changed to vapor, condensation when vapor changed to liquid, sublimation here when solid changed into gas. Okay, but when the gas changing to be a solid, we call it the deposition. To control the amount of the heat that you need or the energy with the specific heat, we are moving through this formula. Q equals mc multiplied by delta T. Q is the heat energy gained or lost. That's amount is measured with the joule. M is the mass with a kilogram. C is the specific heat capacity, and it's a fixed number for different particles. Like each particle has its own specific heat, and delta T is the change that's happening in the temperature, which means final temperature minus first or initial temperature. You have to know that the temperature must be taken with a Kelvin, not with the Celsius. Again, mass must be with a kilogram, temperature must be with a Kelvin, Q, which is the amount of energy measured with a joule, and here the specific heats, it's a joule multiplied by kilogram minus 1 and the Kelvin minus 1. They said here that you have different examples. You can go through it. It's already explained. You can find here the difference that is found for each part and also the amount of the energy that you have to go through it. But you have to take care that the entire energy is being measured with the Kelvin, not with the Celsius, okay? Like here, he has to change it 48 Celsius into normal Kelvin, okay? We have here the last part to go through it, the mole and the particles for the mole. We have here also a relation between Avogadro's number, the number of the particles, and also the number of the mole. Avogadro's number is a constant particle number or molecules number that is found in a specific area. It equals 6.02 multiplied by 10 power 223. We said here that we are comparing any substance with the particles that are found in 12 grams of the carbon that has 12 protons and electrons. You have to understand that the Avogadro's number, it can be calculated from this relation. N is the number of the moles equals N, which is the number of the particles, over Na, which is the Avogadro's number. So we can say that the number of the moles, if you want to calculate it, equals number of the particles over the 6.02 multiplied by 10 power to 23. Atomic mass scaling here, atomic mass unit, it's a 1 over 12 of the mass of the atom of the carbon. Also, it's equivalent to it. The atomic mass here, the unit here, it equals 1 gram over Avogadro's number. Okay, and it's a fixed number. It gives me the ability to scaling or identifying the atomic mass for any object. Molar mass is the sum of the atomic masses found inside the atom. We already know how to calculate it. We have here carbon dioxide as an example. You go directly for the Google particles or the periodic table. Check for the carbon, you will find that the carbon is 12, O is 16, so 12 plus 16 multiplied by 2, which gives me 44. This is the entire molar mass of the entire object or compound. So if I want to get the number of the moles, it equals for me the masses over the molar mass. He can give me the masses here with grams, kilograms, but I would change it to grams. And also molar mass, it's down, which is the number of the uh, atomic masses of the objects found inside the compound. That's all. So we can get the number of moles twice, whether with the number of the particles or the number of the masses and grams or molar mass. You can find here the learning check for each part. You already trained on them. And the last one that we got it yesterday, it's about the pressure. Pressure equals force over an area. Pressure is measuring with the Pascal, and the atmospheric pressure here, it's fixed, equals 1.013 multiplied by 10 power to 5. Any pressure, it's acting over a specific area, and the area is having a force applied on them. You can find that there are different gases law. Boyle's law, it's a relation between the pressure and the volume of the gases when the temperature is constant. And you can find that they are inversely proportional, which means when you increase the pressure of something, the volume will be decreased. So if the temperature is constant, pressure 1 V1, this is the pressure of the beginning of the reaction happening. It equals for me the pressure and the volume number 2, which is the changes that happen later. Okay. Boyle's law here, we have different examples for it. If you want to get the temperature, sorry, the pressure when the temperature is constant, or the volume when also the temperature is constant. On the other hand, we have Charles' law, which is the relation between both the volume and temperature. So before we said P1 V1 equals P2 multiplied by V2. Right now we have V1 over T1 equals V2 over T2, and this is happening when the pressure is constant. That's why we have to change on it and take care of this. Okay. Last thing is the J-Lusac law, which is the relation between pressure and temperature when the volume is constant. So you are fixing one part and you have changing or make a relation between the other two parts. So we have here pressure 1 over the temperature 1 equals P2 over T2. And this happens when, again, volume is constant. From this, you can bring here any missing part.